Okay, wonderful. Okay, great. Thanks for joining, guys. So this is lecture number 6 of the Introduction to GPU Programming Summer School. Today's topic is today's lecture is the last in the series of 6 lectures that we've been talking about that we've been talking about in this course on Introduction to GPU Programming. It's pretty apt that this is the last lecture because this is, in my opinion, one of the most open topics in the area of accelerated programming that we have been exploring and that we are witnessing. So the title of today's lecture is C++ Programming for Generic Accelerators. So the motivation for really, what I'm going to be talking about today is a programming challenge that we are facing today with several flavors of hardware that are available in a real system for us to program. There's a CPU, which is your traditional CPU, which may be x86 based or ARM based, which typically understands a programming model of multiple threads. There's a GPU, which is more, array of discrete processors that can be programmed. It's slightly more like a matrix operation that you can program. There are all these AI accelerators that you can program, which have typically their own independent systolic arrays or different programming model, or an FPGA, which is slightly more complex in terms of programming model, right? So that, as you can see, what's happening is with many flavors of hardware, we are ending up in a situation where there is no common programming language or APIs that can be used to program all these different types of hardware. And additionally, the additional complication on top of this is that there's inconsistent set of tools that are supported from one platform to the other. So if you really want to migrate from your code from running on CPU to GPU, you have to write separate software. As you had seen in the first 4 lectures, you have to write CUDA software that is very specific to a different type, specific class of GPUs that only supported CUDA. On the other hand, from those GPU codes, if you have to migrate to an FPGA, you need to completely redo your application, completely do both your functional port and your performance port to be able to even get things to functionally work on the FPGA, which is obviously a significant detriment to be able to either evaluate or to be able to adopt new accelerators into your system. So that's a very big limitation that specific programming languages give us. And that really is the focus of this class. In this class, I will talk about one of the latest developments that's happening in the world of heterogeneous parallel programming called Data Parallel C++, or DPC++ in short. This is a new programming language or paradigm that enables you to program generic accelerators. I'll cover the fundamentals of DPC++ through several code examples in detail today as part of the first topic of the class. I'll talk a little bit also about unified shared memory, which is a concept where DPC++ has been adopted to be able to program like the traditional C++ style programming, but automatically takes care of translating that into accelerators. This class, as all the other classes have had, will be associated with an assignment, which I believe has already been released by Akshat. The charter of the assignment is to enable you to experience DPC++ by converting the same CUDA kernel that you are using in assignment 5 and optimizing. So it's a very interesting experience to be able to actually program in DPC++ and look at how it actually converts to to the GPU and run it on GPUs. So let's get right into it. So what is Data Parallel C++ or DPC++? DPC++ is essentially your standard C++, which is your standard C++ 11, C++ 14, with extensions to a new standard called SYCL. SYCL is the next generation of standard to enable programming accelerators. This comes from the same group that gave us OpenCL, which is called the Kronos group. DPC++ extends a specific version of SYCL called SYCL 1.2.1, which actually has several cool features. I'll talk about a few of the cool features in my upcoming slides. The way that the DPC++ community is also adopting SYCL is that as they extend SYCL 1.2.1, these features are slowly getting adopted into future versions of SYCL directly, which means that your DPC++, while it requires a specific DPC++ compiler today, in future, once those features get adopted into SYCL, any standard SYCL compiler will also be able to get used by DPC++. And DPC++ is a completely open source implementation, and the goal of DPC++ is to be able to upstream the entire implementation and the compilation into LLVM. so that it can be used in any open source project. And as I mentioned, one of the key powers of DPC++ is that it is built on top of modern C++. And since SYCL is a cross-architecture standard, it really delivers to the promise of one source to rule them all. So with just one source, one programming language source, you should be able to target all those different types of hardware that I'd shown you in the previous slide, whether it be CPU, GPU, an FPGA, or an AI accelerator. And in fact, in our assignment, you'll get a chance to experience some of this. Hopefully, you've done the previous assignment where you would have seen how StudPar can also be used with pretty much the same software to be able to program different types of hardware, whether it be hardware on the CPU or the GPU. SYCL gives you a different type of a control to be able to target other types of accelerators as well, as long as the backend is supported. So let's look at the quick, simple DPC++ program as an example. So here's a simple DPC++ program. It's a simple short program. Right? Let me just quickly walk you through the various constructs here. There's an include, which actually includes the SYCL header. It's available inside cl/sycl.hpp once you implement it. Here, if you walk through the main function, there are a few important pieces that you have to look at. This piece, which is on top, actually starts out with a definition of a variable called R, which is implemented using a standard template library called range that's provided with SYCL. So what range actually does is range takes this one refers to one-dimensional ranges. I'll talk about ND ranges in the next slide, so you'll understand this better. But for now, just assume that R is a buffer of size 16 because number is equal to 16. So it creates a buffer of size 16, and you create a special construct called A, which is called a buffer. It's a special buffer is a special entity in SYCL. We'll talk about buffers also in depth. The core part of DPC++ is a queue, where a queue is basically a particular construct that enables you to submit a kernel to an accelerator. So in this example, you take a queue, and to the queue you submit what you call a handler. And inside the handler, you talk about something called a get access function for this edge for this A. You do an A.get access, which gives you what's called an accessor to be able to control or manipulate this buffer. And then you have this key piece, which is h.parallel for, which is basically a lambda, which lets you actually run the kernel code. Now, it's okay if it doesn't make sense to you right now. We will, in this class, dive into each section of this program in excruciating detail so that by the end of this class, we'll start making sense to what these various constructs are. Finally, once the program actually executes, you go back into the host and you start getting another accessor called A.get access, which gives you an accessor for A. Again, remember A is the buffer here. And then you have a simple for loop that reads the various elements of result, which is your accessor for A, and prints them out in studout. Okay. So just to look at this again, the first portion of the code is actually host code. This is defining the range, defining a buffer, defining a queue, and defining an accessor. This h.parallel for is actually the device code. But as you can notice, it is running as part of a simple function inside your main program. So h.parallel for actually is the piece that runs on the device. And you come back here, and the rest of the code is also running on the host. So as you can see, DPC++ really is writing one simple function that is able to execute, that's able to represent both host code and device code without pulling the device code into a separate function, like what you had to do for CUDA. In CUDA, you'd have to write an underscore device and put the kernel inside it and call an invocation from inside your main function. Here, you don't have to do any of that. It's automatically taken care of by the compiler. You just write straight line C++ code. This is C++ 17 code. And as long as you're able to write straight line C++ code with the right set of constructs, you can actually start parallelizing them and running them on the device. And jumping between host and device is as simple as using the right constructs in DPC. Okay. Again, like I said, at this point, if some of this does not make sense, it's okay. We will dive into the details of each component of this code in the upcoming slides. Okay. So I'm not going to pause for questions, because if you have any specific questions, keep them with you. I will dive into a couple of concepts and I'll come back and then we'll take a few questions. Okay. So let's talk about the various constructs that we'd actually used in this DPC++ program. The first construct is a queue. So you can see here a queue is what is used to decide where to run the kernel code. So that's what a queue is. We'll look at what queues are, how queues are constructed, how to submit kernels to a particular queue in the upcoming slides. The second piece which enables you to share data is called a buffer. A buffer is basically a copy of a particular array that you may have on the host, and you access a buffer through what's called an accessor, which you get by a.getAccess, and that enables you to share data. Again, I'll talk a little bit more in detail about each of these in the upcoming slides. The third piece that was important construct in DPC++ is, in this example, the parallel for, which is basically an example class of a class that used to define a kernel of DPC++. There are three different classes that you can actually use to construct kernels. Either it can be a parallel for, it can be a single task, or a parallel for work group. And each of these constructs will start to make a little more sense when I describe what a work group is. A parallel for, as you can see, just parallelizes and runs as many copies of this as you've defined the range. Okay, that's why you pass the R over here. As many elements are defined in the range, you get that many threads running the parallel for in parallel. A single task is just for one, and parallel for work group breaks it up into work groups. And the key with DPC++ is that each of these constructs, your queue, your buffers, all of those are added as libraries to C++. So you don't need to learn any new syntax when compared to learning C++. So as long as you can code in straight C++, when you have a compliant C++ compiler, you will be able to compile these and run these directly on the GPUs or any accelerators for that matter. Okay. So before I proceed here, any questions that you have? Okay, so let's dig into more detail, right? So like I said, some of these concepts will be new, and as I start digging into more detail, they'll start to become a little more clear. So let's talk about kernel execution in DPC++. In DPC++, data parallelism is actually expressed in what are called ND ranges. Now this will have exact parallels with what you have in CUDA. It's just that the terminology is slightly changed because it's a different programming language. And these ND ranges are what are used in when you define the buffer and the range in the previous example. So you start looking at your overall computation space, and your computation space is called an ND range. And the dimensions of the computation space here are 3 dimensions, dimension 0, a dimension 1, and a dimension 2. So your ND range cube is your overall total set of work that's available that has to be executed. Your ND range is typically broken up into work groups. Right? Your work groups is basically, in this example, looking at a 4x4x4 work group, which is a cube. So here you have a 4x4x4 work group that has 3 dimensions, 0, 1, and 2. Each ND range work group has subgroups. Your subgroups basically, subgroups in a work group, the reason why they're important is operations like barrier sync, much like what you have in CUDA, can be defined on a subgroup and a work group boundary. So you can actually put barriers that say that, okay, all the threads that work on the subgroup, once they come to a certain point, then the rest of the execution can continue. And you can also do this on the work group, at the work group granularity. So the parallel for that I spoke about in the previous slide, it's a parallel for work group actually creates parallel fors for each work group, right? Not for the subgroup, but at a work group level. And your regular parallel for creates parallels in the entire ND range. So that's the difference between work group and overall ND range. And the subgroup is further broken up into each element. And when you write your kernel, you're really writing kernel for every item in the work group. So you're writing it for a single work item, and that gets composed into the subgroup, into the work group, and into the overall ND range. So if you look at it in terms of total work, the total work is number of work groups, is defined by this cube, times number of work items per work group, which is defined as number of subgroups, into size of each subgroup. So that's the total work that has to be done in the ND range. And using a combination of parallel for or parallel for work group, you can actually launch kernels, and the kernels are written with the idea of each range in the idea. Again, remember, right? This has exact parallels with CUDA. In CUDA, when you program a device, when you write underscore underscore device underscore underscore and write a kernel, you're programming it from a perspective of a single thread, which is what we call a work item over here, right? And your subgroup has parallels with warps, and you have parallels with work groups and with ND ranges with CUDA as well. Okay. Any questions on this particular concept of ND ranges, which has direct parallels with what's there in CUDA? Right? Okay, so let's talk about this interesting concept of a queue, right? A queue is actually a very interesting concept. Okay, so make sure my recording is on. Okay, so let's talk a little bit about queues, which is one of the important concepts of actually executing kernels on a DPC++ device. So a queue is essentially the construct that enables you to decide what needs to run on a particular target. So a work for a particular device is submitted to a queue, and each queue has specifically one target on which you want to run a particular code. However, a given device might have multiple queues that feed into it. Okay, so the idea is that from the host code, that is the DPC++ code that you saw earlier, you take a queue which corresponds, the queue that you select automatically dictates which device you're going to run on. You throw the kernel into the queue, and then from the queue, it executes on the device and comes back. And the host doesn't have to care about anything about how the queue gets scheduled to the device. Is completely a property of the runtime. You have several ways by which you can actually select queues. This is the default way where you create a queue targeting any device where you do a queue. There's typically a default queue that's defined depending on the device and the way that DPC++ was built. However, you can also create queues targeting very specific devices. So you can create a queue that's targeting a CPU, which is selected by using what's called a CPU selector. You can create a queue selecting a GPU selector that decides that you're going to run on the GPU. So Q1 here would have been selected with something like this. You can create a queue which can do an FPGA selector, right? So if your runtime supports Intel : FPGA selector as a function, you can actually do that, and you can get a queue with which you can actually target to run something on the FPGA. Right? Your runtime could also export a function called accelerator selector. If it exports something called accelerator selector, that gives a particular queue. For that accelerator, there's a queue that's defined, and you get a handle to that queue, and you can submit stuff to that queue. And remember that for every DPC++ executor, there needs to be a host. So queue of host selector, which is the default, will always be available. And the idea with the queues is that once you submit a kernel to a particular queue, multiple kernels can be submitted to queues, and the kernels can execute in any order. So you don't really have control over what order the kernels are executed in the queue. In some ways, you don't want to have control because you want the device to be able to figure out which kernels are ready to execute and execute them as and when they're ready based on data flow. So we'll talk about a particular example about order in which kernels may be executed. But the thing to remember is that once you put something into the queue for a particular device, the order of execution is not guaranteed to be the same order in which you queue the kernels on, as long as data flow dependencies are honored. So in that sense, it's not truly a queue because a queue is a first in, first out, but this is more a data flow dependent queue. So it's, that's just the terminology of it, but a queue is a good way by which, it's an abstraction by which you can target executing on a particular device, and you don't have to care about how many threads and etc. Just put it in the queue. The queue scheduling will take care of it, and as much parallelism as possible. If multiple kernels can be run in parallel, the device will automatically do it and come back without a problem. Okay, so that's what a queue enables you to. So let's look at one more, extension of dependency graphs on kernels based on queues. So let's take this particular example. So in this example, you have, it's very similar to my previous example. It's slightly more elaborate. You have you define an ND range, which is just one dimension of, let's say, number 16. I define two buffers here, A and B. Remember that buffers are copies of the range that you determine here that are used for access from a device. Okay, just think of a buffer that way. I have a queue. There's no constructor call, so default constructor is initialized, and it targets some device. Actually, you don't have to care. As long as the programmer goes, you want to run it to a device, let's assume the queue is the right queue for the device. I have 4 submit functions, each of which submits a different kernel. You have queue.submit that gets A, which takes the buffer A, gets an accessor to it called out, and submits, updates out. I have kernel 2, which again gets an accessor to A, calls it out, and updates out. I have kernel 3, which gets an accessor to B and does some operations on B, and I have kernel 4, which gets access to both A and B, and then does some operations on both A and B. Okay. Now, remember I told you that though you submit the 4 kernels in sequence from your program, execution may be out of order. But can anybody guess what the execution order will be here? Or will it be completely random, or can we do some prediction on what the execution order may be? Somebody want to take a guess on what the execution order may be? Will it necessarily be 1, 2, 3, 4? Okay, so let me start with the answer, right? So essentially what actually happens here is that the queue to which you submit all these 4 kernels takes a look at the data flow between these 4 kernels and identifies that A and B are actually working on A, so kernel 1 and kernel 2 are actually working on A, right? So there is an implicit data flow dependency between them. Kernel 3, on the other hand, is working on B, which has no data flow dependence on A. So you can execute kernel 3 in parallel with kernel 1 and kernel 2. And kernel 4 has a data dependence on both A and B. Therefore, kernel 4 can execute only after both kernel 2 and kernel 3 have executed. So the way that the kernels will be executed will be done such that you honor this data dependency graph when you execute them on the device. And that's automatically implicitly taken care of by the runtime. So you don't have to worry about constructing this graph offline in your code. It's taken care of by the fact that you submitted all these 4 kernels that operate on these 2 buffers to the same queue. And that data dependence is automatically taken care of by the runtime, the DPC Program runtime. Okay. Okay. Any questions on queues before I jump to buffers and other constructs in DPC++?
Yeah, Pradeep, one question.
Yes.
Yeah, so this kernel 1 and kernel 2, so the runtime totally avoids the data race between the two. Is that how it is happening?
Yeah, the runtime does not know anything about the data race, right? That's why it actually executes them in sequence.
I see.
Actually, if you look at the program over here, you don't even have to run kernel 1, right? Because kernel 2 is the same as kernel 1.
Right.
Okay. Right. So it doesn't guarantee, if there's a data race between the kernels, that's up to the programmer, right? The runtime doesn't know anything about it.
Oh, I see. So because we are writing to the same memory location, therefore kernel 2 cannot execute.
It executes them in sequence.
I see.
Yes. That's to execute them in sequence.
So even if kernel 2 would have been, sorry, kernel 1 is reading from a memory location, which is probably previously written, and kernel 2 is writing to the same memory location, still there will be a sequential execution.
There will be a sequential execution, yes.
Sure, sure.
Yes, so the data flow has to be followed. The order in which you submit, it assumes that the data flows in that order. So there's a dependence because of data flow, it takes care of that automatically.
Sure, thank you.
Okay, all right, so let's move on to buffers. So the buffers are the second construct that's important in DPC++ to be able to access, to enable devices to access the data that's created by the host. Now we go back to our original example. I will use this example for the rest of the slides because it's the simpler example. The previous example helped me understand different kernels. But here again, you have a range. You create an R, which is a range of 16. Create a buffer A. You have a queue.submit with an accessor and a kernel with a parallel for, and you get a get result. Okay. So a buffer, essentially here we have created a buffer A of R. What it does is a buffer is an encapsulator, which encapsulates the data that is inside R. Okay. And the buffer is the construct that SYCL runtime manages, which has a copy of the buffer R, of the data structure R inside the buffer. What's the right way to say it? So inside the buffer construct, there's a copy of data structure R. And to be able to access the buffer from different devices, you need to do a buffer.get access. which gives you what's called an accessor. And when you get an accessor, you can define what mode you want to access the buffer in. Do you want to access the buffer in a write mode, or do you want to access the buffer in a read mode? Now, what this actually lets you do is it lets the runtime understand that, for example, in this example, you have a h.parallel for it's a kernel that's coming up that's going to be using the buffer accessor, and you're going to be writing it. So this means that there has to be a data movement from the host, which is where this is created, to the device, because the device is going to write to it. And that written update has to come back when you come back to the host, when you try to read it. On the other hand, if all you did was to get an a.getAccess of read here, and you use that inside the kernel, there has to be a copy that goes from the host to the device. But then you don't have to get a copy back, because it's just using for read. It's just used for reading, and once it's read and the kernel executes, you can throw the result away because it's not going to be read anymore. So the accessors are a nice way by which the programming language or the programmer tells the runtime in what way am I going to use the buffer. If you don't tell it in what way you're going to use the buffer, conservatively it has to assume that it has to always read. So it'll always have a write. So you'll always have to make a copy back. But through this accessor, what you actually get is it's a very simple way by which it tells the runtime, am I going to be writing it, or am I only going to be reading it? If I'm only going to be reading it, I need to make it available in the device, but I don't have to bother to make a copy when you come back from the kernel. That's a very big advantage. And the location of the buffer actually depends on the accessors, right? Like I said, if you're going to write, you need to make a copy and get the copy back and update the range R. That's why when you come back, you get an access result. And when you do a stood out of result of I in the host, remember this executing on the host, you actually get the data back for A. That's because when the parallel for kernel actually returns, you get the data back on the host for this. And all this movement between the CPU and GPU or CPU and accelerator is completely taken care of by the runtime. As long as an accessor very clearly defines the mode of access, it's a very seamless, performance optimized way by which buffers are handled for sharing data between CPU and the host. So the other thing to also remember is that there is, although this is a linear piece of code that you see here, there is some amount of asynchronous execution happening as long as data, again, as long as data dependencies are maintained, just like we saw earlier. Okay. Here, what actually happens is, remember, if you remember from the first slide, the creation of the range R, the buffer, and the queue are all on the host. The h.parallel for is actually running on the device. So the way the host execution actually happens is it goes statement by statement. Once the h.parallel for actually comes in, it issues a command to submit a kernel to the device, and then the control actually returns back to the host. So technically here at this point of execution, the GPU may be executing something or not yet done with executing this full parallel for, but the host can continue executing on something else. Now, since we are getting an accessor to the same buffer that's being written by the kernel, there's a data dependence here between the host code and the device code. Again, you should read this code in sequence, right? A.getAccess, you're writing, and A.getAccess, you're reading. It's the same A dot, which means it's the same buffer. So there's a data dependence between the device and the host. And because of this data dependence, this A.getAccess will actually wait for the h.parallel for to finish on the device before you actually can execute anything back on the CPU. But if you're not going to wait on this A.getAccess, you're not going to wait on A, which is essentially modified by out here, you can actually run anything else over here. You can run any other code that you want to run on the host without any problem, right? The management of what is run in parallel, what is run in sequence is completely handled by runtime as long as data dependency is handled, right? Again, what DPC++ is really making you do is it's telling you, don't think of execution as sequential and parallel. Think of execution as data dependencies, which is truly what the programmer should be thinking about, right? Program it as if it's a data parallel machine, and the runtime will take care of executing some stuff on the CPU and some stuff on the GPU or the accelerator. And it will parallelize as much as it has to. But from a programmer's perspective, you as the programmer should not worry about what is sequential and what is parallel. And that's the beauty with DPC++. It's forcing you to think in a data parallel way as opposed to sequential and parallel execution. So it's giving more power to the programmer and letting the runtime do the heavy lifting of moving data between host and device. You'll see here, right? There's no CUDA mem copy. There's no host to device copy, device to host copy, none of it, right? All of it is taken care of by this buffer and the get accesses. All that is completely handled by the runtime. The launch of the kernel is handled by runtime. We don't have to do any of that activity. Okay. All right. So these three concepts that I spoke about, right, which is your device queues, your buffers, and an asynchronous execution, are the three fundamental building blocks of any DPC++ program. And with these three concepts and a very simple example like this, you really will be able to program in DPC++ and target different accelerators. Now, again, the assignment will give you a good handle on trying this out, and with very simple examples, which you'll be able to play with. But this is the fundamental concept. I'll talk about one more thing, which is about unified shared memory, which is a slightly, making this even simpler, but not as performance optimal. But before I go there, are there any questions on this particular slides? Yeah. There are no questions. I will continue. So let's talk a little bit about the second topic that I wanted to cover in the land of DPC++, which is called Unified Shared Memory, or USM. So the concept of buffers that we just spoke about is the preferred abstraction for memory in DPC++. Right? In fact, it is the only abstraction available from SYCL 1.2.1 because they wanted the programmer to not worry about whether the data is allocated on the CPU or on the accelerator, how to move data between CPU and accelerator. They did not want the programmer to worry about it. So they said, if you want to use SYCL 1.2.1 and program with it, buffers and accesses were the only method of accessing it in SYCL 1.2.1. However, programmers are used to unified shared memory, right? Which is, what is unified shared memory? Where you do an allocate with malloc, you deallocate with free, and use pointers to move back and forth. So the question that the DPC++ community was faced with is, can we extend the concept of unified shared memory to be able to use malloc or a modification of malloc to actually allocate memory and then to use pointers? Okay. So DPC++ actually implemented this extension called Unified Shared Memory, or USM, that enables programmers to be able to allocate and free memory just the way that they're used to. So USM is actually an alternate way to buffers for memory management in DPC++. So let's look at a very simple example with USM. Now, if you look at this example quickly, this will actually look a lot more like your traditional C++ code when compared to what I showed you earlier. So here you have two buffers or two arrays that are created using your typical malloc. Now this malloc is not just malloc, it's called malloc_shared. I'll tell you what that means in a minute, but let's just assume that it's malloc. So you create A, which is an int star created with a malloc, and you provide your typical n times size of int, whatever, etc., other functions, other arguments that malloc shared has. Now you then go back to a q.submit. Remember this DPC++ code, so you still have to use q.submit to handle or to submit kernels to a particular queue for which you've been given a handler. And inside the handler, you have a parallel for to launch a kernel. But now inside the parallel for, to get access to A and B, I don't need to create any more accesses. All I do is inside the parallel for, I just do A star of I, A of I star equals B of I, which means that I am actually accessing the buffers that are allocated in malloc using just pointers like I've used to always. So I don't have to create an accessor, or I don't have to do any kind of read or write accessor creation to be able to access these buffers, but I directly access them using pointers. So the beauty with USM is that you can actually very quickly convert code that's written for straight line C++ into DPC++ code using unified shared memory. But a big caveat is that USM is not expected to give peak performance. It's a good starting point for conversion. I'll tell you why that is in a little bit. But this is a good starting point for conversion. But to really get performance from DPC++, you need to start using buffers and accessors. Okay. So there are a few allocation types that are actually handled by unified shared memory. You can decide that the allocation is done on the device only, or the host only, or it's done as shared. And for each of these types of allocation, there is different restrictions on who can access it. For example, let's say that you allocate a memory on the device. Okay, let's say this host of this device. I use a malloc underscore device, which is the key for allocating on the device, and you do a device allocation. What this means is that this memory is only accessible inside the device, and the host cannot touch this memory. So if I do a malloc underscore device of a particular array, I can use the pointer from that malloc inside the kernel. So I'll come back here, right? Like for example, here, if I created A and B and I replace the malloc underscore shared with malloc underscore device, I can still do A star of I, A of I star equals B of I, because inside the device kernel, remember parallel for is going to run inside the device. I can do that. But if I come back to the host code after the q.submit, if I try to access A or B, I'll get a sec fault because it is divided. If it is allocated to malloc underscore device, I will not be able to access it to the host. Okay, and similarly, you cannot migrate. Let's ignore this migratable to for now, right? The migratable to actually dictates whether the overall buffer can come back to the host or move to the device after the kernels execute. We can ignore this for now. Let's just focus on the accessible byte column here. The second type of allocation is your typical allocation, which is done as malloc, right? In malloc, or it's called malloc host, where you do a host allocation. Now, the beauty with malloc host is that what happens is a buffer that's allocated on the host is accessible by any device. However, a copy of that particular buffer will be made to the device, and when the kernel finishes execution, that copy will come back and update whatever is there in the host. But if I have 2 or 3 different accelerators, all of which want to access the same buffer, what you do is you'll allocate on the buffer, you let the first device access that buffer, make the modifications, comes back to the host, next let the next device allocate it, so on and so forth. Okay. And again, here you cannot migrate it because, again, migration has to do with performance optimization, and these are not migratable to the host. This buffer is owned by the host and remains in the host. It never moves. The third allocation is called a malloc underscore shared allocation, where you can access it both by the host and the device. However, if the access is only from the host or if the access is only from the device, the allocation actually moves to be performant like a device or a host malloc. So you do a malloc underscore shared, and if only the kernels inside the device are actually accessing it, then the malloc actually does not create memory inside the host, but actually creates memory inside the device. That's the benefit with malloc underscore shared. Now again, remember, right? USM is provided as a mechanism by which one can allocate memory in the device or in the host as an alternative to using buffers and accesses, but it is not expected to be as performant as buffers and accesses. So before I open for questions, I'm going to walk through one slightly bigger example that actually shows how to use malloc shared and the various constructs that are associated with it. So let's take this particular example. This is a full USM example where you actually create 3 different arrays called A, B, and C with malloc shared. So this is where you declare USM array. Here in my example, green means you're allocating it initially on the host. Right? So these are going to be initially allocated on the host. You initialize the arrays. Remember, this is host code because you're running outside the q.submit. It's not a parallel for. So on the host code, because it's allocated with malloc shared, you can actually do simple pointer based access. A of I equals I, B of I equals twice I. So very easy access. Now, inside the parallel for, I create a kernel, and in the kernel, I can actually do C of I equals A of I plus B of I because these are declared as malloc underscore shared, which means that I have access to these USM buffers also inside the device. Okay. And at the end of your q.submit, when you do a q.wait, it waits for all the kernels of this queue of this particular queue to be emptied. Now, once that happens, because this is malloc shared, this queue, so these buffers are actually allocated on the host, and A, B, and C, which are initially on the host, are actually updated and ready to use with the updated value as created by this kernel inside the device. That's the brilliance of malloc shared, where the data movement is also implicit and you don't have to worry about it. Okay? So one question to anybody who wants to take a shot at answering, can we replace malloc shared with malloc device or malloc host? Will either of these work based on your understanding so far of malloc device and host? Anybody wants to take a guess?
I'll try this. So C can be malloc device.
C can be malloc device, yes.
Whereas A and B.
But you can't access C outside.
Yes, we won't be able to use it later after Q dot with. That is yes. But A and B
can be malloc.
Yes.
That's correct. Yeah, if you do A and B as malloc device, the problem will be that this particular, if you do A and B as malloc device, this access will not work because you're trying to update it from the host code, and therefore that will not work. Right? And so yes, A and B has to be malloc shared or malloc host. C can be made into malloc device. So what we've also done here is I've taken the same example as I had earlier and converted the same example into a buffer so that you understand how different it looks. So here's an example of the same example as buffer. So here we just use traditional malloc for the three arrays, A, B, and C. It's no longer malloc shared device or host, it's just malloc. And then malloc puts it on the host. So you declare C++ arrays, A, B, and C with malloc n into size of. You initialize the C++ arrays. Now these are typical pointer-based arithmetic that you're doing on the host. You create buffers, which is your preferred method by which DPC++ wants you to access these arrays. Now these are created using a combination of a range kernel that you need to define depending on how many parallel elements you want to execute together. And these buffers are called AB, BB, and CB. Now inside your kernel, you create an accessor for the buffer, which dictates what is the mode in which you want to access this buffer. Do you want to access this buffer in a read mode? Do you want to access this buffer in a write mode? And then inside your kernel, you actually use the accessor. Now remember, the brilliance of this is that here you have not really said whether it should be a malloc device or a malloc host. But when you define the buffer and you define an accessor, the runtime figures out, should this be a malloc device or a malloc host, and automatically takes care of migration and allocation. So here, what will actually happen is that this buffer copy that you actually have over here is only created in the device. There's no copy on the host initially, and then you come back and then you update the host over. Right? So what this accessor, again, just to reiterate, what the accessor actually lets you do is, here, the copy of A and B that actually is taken inside the GPU does not have to come back to the CPU because you're only going to read them. You're not going to write into them. However, in the malloc shared example that I showed earlier, you need to bring the copy, although there's no update that's happened in the device, the runtime does not know it. So there's actually conservatively a copy that has to come back to the host for updating A and B, although there's no updates that have been run to A and B. But with DPC++ accessors, you are explicitly telling the runtime that, hey, I'm not going to touch A and B. So you can create a copy in the device if you want, but don't bother bringing it back to the host. So the consequence of this is that the overhead of making copies between the CPU and the GPU are not there, and therefore you get better performance with buffers when compared to using USM. This is again something that you will experience in your assignment, where we have asked you to create the same example using both buffers and unified shared memory, and you'll really be able to experience the difference in performance between these two examples and understand these in more detail. Okay. Any questions on buffers or USM? Okay. If not, actually today is a small class because DPC++ is a fairly extensive topic, and I've already thrown a lot of concepts at you today, so I don't want to spend a lot more of your brain time looking into this. So I'm going to conclude today's class a little bit early and let you go back and read up about these topics in more detail and start working on the assignment early. So DPC++ is a cross-architecture language to program accelerators. It extends SYCL 1.2.1. It really is it's challenging the dominance of CUDA to target accelerators, right? And there are actually tools out there that enable you to automatically convert from CUDA to DPC++, giving you a lot of advantage in terms of how to program DPC++ and to get a starting code that's functional with DPC++ and then to optimize it from CUDA. There is a lot of active community development going on in DPC++. In fact, DPC++ now also supports the execution policies that I discussed in the last lecture. So I'd encourage you to go back and look at some of these, the talks that talk about execution policies and how they get supported in DPC++, so that you understand them in more detail. Some references of stuff that I'd used, right? There's two very good talks from Intel on DPC++, introducing you both to the new programming model, which is DPC++, that's a part 1 video, and a part 2 that talks about best programming practices. That goes a little bit more into what are the advantages of using USM over buffers and why buffers are better than USM. So I'd encourage you to go back and look at some of these videos and understand this. And also the reference book, it's a good big book, fat book. There's a PDF, free PDF available online if you want to go and find it. So next steps for you really is to dive deep into DPC++ is assignment 6. The one thing I want to highlight in this assignment is that unlike the other 5 assignments, since you need access to Intel GPUs to run DPC++, you need to use a different compute environment called the Dev Cloud. So the assignment that we've released also has details on how to access Dev Cloud and how to run code in it. So you'll not be using Google Colab. We have a tutorial session on Thursday, 5 to 6 p.m. In the same link as what's being used for this class. I encourage you to dial into this tutorial section, especially since it's a new development environment. There may be some questions. Please dial in. We'll have Akshat who will also be dialing in for this tutorial section to give you a little more clarification on the various topics over there. That's really all I had today. So again, this is the last lecture in the series of the summer school that we've been conducting. So we'll open the floor for any questions either to do with this particular topic or any of the topics that we've covered so far in this class. Now. Are there any specific questions that anyone has that anyone wants clarifications to? Okay, if there are no questions, we actually have an early end to the class today. That's all I had, Rupesh, from my side. Any closing remarks before we actually close early today?
Nothing more except that if participants have, we are all aware that both CUDA and DPC++ are considerably deep topics, and it does take time to learn all of these. We have tried to convey some parts of it, but of course there is a lot to learn. But if you have any specific feedback about what topics we could possibly cover in a future session, or should the session duration be longer, for example, this course duration should be longer, please feel free to let us know. Just write to any of us and that should be fine. Yeah, there is a question.
Yeah. So the question is, when running CUDA code with NEC++, what's the difference between stdpar and -TA equals Tesla? I'm not familiar with the -TA flag, Rupesh.
Yeah, so that is probably the target architecture. So that Tesla is specifically for the GPU, that it targets a particular architecture. This is borrowed, I think borrowed from OpenACC, where that -TA can allow you to generate code either for the GPU or the CPU also. Right. So I think for different families, like for me, you might be able to specify a different target architecture. But stdpar should be generic, and although this is NVC++, so it's NVIDIA specific. But stdpar, I'm not sure whether these two are equivalent. My feeling is that
it won't be equivalent, right? So yeah, stdpar will be. Stdpar, of course, is NVC++ specific, but if there are specific optimized kernels that are available for Tesla architecture, they may kick in when you do --stdpar -Tesla -TA equals Tesla, right? But it's possible that for some other kernels, what ends up happening, Balakrishna, is that for specific architectures, the lower level implementation of the library kernels tend to be for important GPU families or GPU architectures. They'll have separate implementations that are performance optimized between the Volta or the Tesla and the Ampere GPUs. So if you select a particular target architecture, the right library for kernels or the right combination of assembly instructions from your CUDA kernels get selected when the CUDA kernel is actually compiled, but as opposed to a generic schedule, right? I think between STUDPAR and TA Tesla, it's just orthogonal. I think both of them using together, you may find that not using STUDPAR without TA Tesla or STUDPAR with TA Tesla, there may be a performance difference if there are kernels, if there are library functions that are optimized for Tesla or not. I hope that answers your question. Okay. Okay, thank you everyone for the attendance. It's been a pleasure teaching this. First time we're doing this DPC++ and STUDPAR, I should say. It's been a learning exercise for us as well. We hope you find the assignment to be interesting. Thank you very much everyone for your time. Thank you, Rupesh, for the opportunity.
Thank you, and also thanks to Ashwin, Akshat, and Deb for helping us in taking care of the assignments.
Okay, thank you.
Thank you. See you. Bye.
Thank you, sir.
Thank you. Thank you, Shriya Krishna. Thank you, Balkrishna. Thank you for submitting the assignment, by the way. Okay, I'm going to close this meeting now.